All right, so we're going to begin our discussion of the structure of the atom. So, along with this lecture bit, I'll be posting to Moodle a outline on the chemistry of small molecules, and that's what we're going to be doing today. For this next little bit, is discussing some basic structure of the atom, and then tying that into a little bit about atomic bonds, how atoms are stuck together, because that actually is going to play a really important role in terms of the strength of these different bonds as we start talking about these different molecules like proteins and carbohydrates. So, the structure of the atomic bond, the atom. And one of the things I find a little interesting is that when we start at this level, at the structure of the atom, this is very small. Yes, there are subatomic particles. We ain't talking about them, because you kind of, every time you go, okay, atoms made up of protons. Well, what are protons made up of? Well, they're made up of mesons and leptons. Oh, what are they made up of? They're made up of, I think when you get down to the bottom, it's actually made out of dust balls. I don't know. And so when we start talking about macromolecules like proteins, carbohydrates, nucleic acids, I actually have a tangible feeling for that. I mean, I actually manipulate these things, and I, can extract proteins and individual proteins and think about them. And these large molecules, what are called macromolecules, they actually can affect the consistency of water. Like we're going to see here that carbohydrates are responsible for putting the pud in pudding, making pudding thick. But when we get down to the structure of the atom, there just isn't anything there. And it kind of always slightly freaks me out that really when you start thinking about it, there just is nothing solid here. Theoretically, there's enough space that I should be able to vibrate through this desk, kind of like what the Flash does. So if you've seen your Avengers and you know about Ant-Man going down to the quantum level, we're not going down quite that far. But we are going to go down to the structure, to the subatomic level, and think a little bit about what makes up an atom. So I'm working on my new marker technology. We'll see how these go. There you go. All right. So when we get into the atomic structure, we have three basic particles. So in terms of conceptualizing the scale and things, let's think about this. Imagine you're on a football field and you're standing on the 50-yard line. Now, further imagine that you're in a domed stadium. So I was thinking about the Astrodome. And, it's like 300 feet up, and there's the skyboxes and lots of people can fit in here, lots of seats. We're social distancing, so there's nobody in there. In fact, it's completely empty, just you. Now, also imagine that this sphere continues down below you. So it's not just a dome, it is a sphere. And you're standing suspended in this sphere. 300 feet above you, 300 feet below you, lots of space. We're on a football field. Now, imagine that you've got something the size of a basketball, and we're going to put a plus sign on that. So here is our basketball with a plus sign. Take that basketball, boom, 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 put it down the 50-yard line. That basketball is a positively charged particle called a proton. Now, take another basketball, put an N on it, and this is a neutron. It has no charge. It's free, no charge. Now, further, let's take a ball the size, between kind of a ping pong ball and a tennis ball, a racquetball. And let's put a negative charge on that. And now with all your might, throw that into the ceiling. And it begins zooming around the proton and neutron. This is going to have a negative charge. This is the electron. Now, the real truth is the electron is zooming around the proton and neutron, which make up the atomic nucleus. And the electron is forming the dome. There really isn't a dome. It is, in fact, the track the electron is taking. And, you think about this, there's a lot of space here. You got two basketballs, a little tennis ball zooming around. You're standing in the middle of a hydrogen atom. Now, here's one of the things that is important when we start thinking a little bit about the names and the way we think about chemistry. The elements are the different atoms of all the known elements on the planet and the universe. And these elements are based on the number of protons. And so here's an important concept, in that an element's identity, and I'm trying not to block the camera, but here, I'll write for a second and then we can get out of the way. An element's identity is determined by the number of protons in the atomic nucleus. All right, so what that means is if we add another proton here, we've changed the element. We went from one proton, hydrogen, to two protons, helium. And let's think about this for a moment. Hydrogen is what caused the Hindenburg to blow up. Hydrogen is great rocket fuel. Helium, completely inert, will not catch fire. It's actually what they use to pressurize rocket fuel. Helium and hydrogen are identical, except helium has got two protons, hydrogen has one proton. And in fact, not to belabor the point, but you don't even have to have the same number of neutrons. You can change the neutron number and not change the element's identity. And one of the ways we can phrase this is if the number of neutrons doesn't equal the number of protons, this is called an isotope. Now, some isotopes are radioactive, meaning they actually will decay or kick out particles. Some are phenomenally stable. And it turns out the most common form of hydrogen on the planet is in fact an isotope. It looks like this. There is a single proton, but no neutron and no electron. It is in fact just a proton. And so we'll be talking later in the semester about protons and proton pumps and acid protons and things. And just keep that in mind is that we're talking about a hydrogen ion. So, hydrogen. And as we start adding more basketballs on that 50-yard line, we're changing the element's identity. So at this point, you've seen, maybe watching Breaking Bad, the periodic table of the elements. And these are the different elements based on the proton number. And they go 1, 2, 3, 4, 5, 6, 7, 8, just keep on going up. And what's kind of interesting about this is that you got elements like oxygen that are critical for survival. You have elements like arsenic that are incredibly poisonous. And they are both made up of the exact same thing, protons and neutrons. And that always makes me kind of go, really? But it is. So at this point, I think there are about 75 or so naturally occurring elements. And then using giant cyclotrons and atom smashers, you can bam things into each other to add more protons to that football field, and you can make what are essentially non-naturally occurring elements. At the moment, the biggest one is about 110 protons on that football field. It's not very stable. It tends to blow apart pretty fast. There's actually an idea that there are these proton stable island numbers that you got to get up to about 120 or so. But if you think about a football field, we should be able to put a lot of protons onto that football field. And I mean, it's sort of a technological thing, but there are probably materials that we'll be able to invent that'll be kind of like Star Trek's duranium or something that might have interesting properties as we're able to get more protons onto that football field. Now, that's the atomic nucleus. Our next topic, though, is going to be atomic bonds. Now, we're not talking atomic bombs. We're talking atomic bonds. And these are the way atoms can stick together. And we've got 3 different primary atomic bonds. And they have a strength related to them. So we're going to start with the strongest bond and work our way down to the weakest bond. So the strongest bond is what's known as the covalent bond. The covalent bond is defined as an equal sharing of electrons. All right, now let's think about this. A couple of truisms come from this now. First off, the amount of energy that it takes to break a bond is equivalent to the amount of energy that it takes to make the bond. And so thinking about how much energy does it take to break a bond is a way of thinking about the bond's strength. And it turns out that with covalent bonds, about the only way you can break them is to set them on fire. Now, for the purposes of biochemistry, I am here to tell you that that ends up being about 450 degrees. Just as a general truism, if you're baking something below 450, it might brown, it might dry out, but it's not going to char. You get above 450, now you could actually get some charring going, and if you're not careful, whoosh, you'll catch on fire. So most organic molecules, most molecules that we would eat, the covalent bonds are going to break apart around 450 degrees. So that's pretty darn hot. You know, you're not going to find a place naturally occurring on the planet. And, you know, in terms of our body temperatures, you're never going to find that. So we'll get to how we can manipulate these bonds in different ways later, but for now, that's the way we can think about this. Now, so a covalent bond, it is equal sharing. And essentially what we got is an atomic nucleus. We'll make a helium ion, or a helium atom. So we got 2 protons and 2 neutrons. And here's the electron zooming around. And now let's take another helium ion or atom. We got the proton here, positive charge, the neutron, and there's the electron. Now what we got to do is get these 2 atoms really close to each other, and then the electrons can they can start playing tag. They'll start chasing each other. Let's think about this for a second. You know from a pretty good analogy is like a magnets that have the opposite poles. The opposite poles will attract, but if you've got like poles, they repel. The same thing is happening with charges. Opposite charges attract, like charges repel. You got 2 negative charges, they're going to be repelling each other. Ooh, you repel me. And so what we got to do is overcome that repelling force to get them close enough that the electrons are now dancing together. So that's what takes the energy to make a covalent bond, and then the energy to break that apart is what we're talking about with the fire. So we can imagine, say, a dome stadium here in Decatur with the basketballs and the little black, or the, I'm thinking like a racquetball, black rubber, a rubber racquetball flying around in the big dome here. And then let's go ahead and put one in Bloomington. Now, what we got to do is bring these two domes close enough together. So we'll leash up a herd of dachshunds to each one and start them guys moving. Something's got to push them together. In our case, it's the dachshunds. They're yipping and yipping, and they're getting closer and closer. Now, as we start getting towards Clinton, the midpoint, we're going to start having some repulsion forces. And it's like, come on, you guys, you got to make it, and you got to push, you got to push, you got to push. And then all of a sudden, wow, they slam together, and you've made a covalent bond. So you have this repulsive force you have to overcome. But once you do, stick together, and you have made a covalent bond. Yay! So pretty much any bond worth breaking is a covalent bond. The other two bonds, comparatively, are so weak that they fall apart if you look at them funny. But covalent bond, that's our number one strong bond. So I'll ask you, what is the strongest atomic bond? And you will respond, covalent bond. That's it. Very good. All right, number two on our hit list is how long have I been guessing on? 16 minutes and 58 seconds. Yeah, okay. Number two in our bond hit list is what's known as an ionic bond. An ionic bond is now an unequal sharing of electrons, i.e., we've got an atom that has an extra electron and then an atom that is missing an electron. So let's look at this. Two atoms that can form ionic bonds make salt, and that is sodium and chlorine. Now sodium, which its chemical symbol is Na, sodium is missing an electron. Compared to the proton number, it has one electron missing, and so its charge isn't balanced. It ends up having a positive charge. Chlorine, on the other hand, has one extra electron and ends up having a negative charge. And so we have chlorine over here saying, I'm so sick of these damn electrons. I wish it was somewhere else. Go someplace. I got too many electrons. I don't know what to do with them. And then we got sodium over here that goes, I so wish I had an electron. I so need an electron. I'd pet it every day. So, sodium and chlorine, they get together and they can form this unequal sharing. So let's define that here, just we didn't, of an unequal sharing of electrons. And atoms that have a charge, either they're missing an electron or they have an extra electron, are referred to as ions. And so this is called an ionic bond. Now, the ionic bond then is fairly easily disrupted, fairly easily made. In fact, if you take ionic bonds and throw them into water, they will dissociate into ions. Now, just as a little point, I don't know if we have any ceramic people out here, but there is a kind of pottery known as raku pottery, in which you take your pots, you put them into the kiln with lots of fire, like 1500 degrees or more, and you can throw salt, rock salt, into it, and it sprays these really cool greens and things across the pot. You want to be careful you don't take a big sniff when you do that, because you're generating chlorine gas. But it's a way of generating some interesting stains on the pots. Now, here's the thing. To break salt apart requires really high temperature. 1,500, 1,800 degrees. I don't know what the exact degree is, and you don't need to worry about it. But it's like, like blowtorch hot. And yet, we're calling this the second weakest bond? What the heck? Because covalents break at 450. If these break at 2,000 degrees, how are they weaker? Good question. It's because in a dry atmosphere, an ionic bond is very tough. But in water, ionic bonds are very weak. And that's one of the key differences between biochemistry and plain old chemistry, is that biochemistry is the chemistry of molecules in water. And so that's why ionic bonds are number 2 by a long margin from covalent bonds. So we can break apart ionic bonds. Another example, think about, is if you throw salt into water, it dissolves, right? Okay. Now, when it dissolves, it's actually dissociating. On the other hand, if you throw sugar into water, it dissolves. That's actually not the same thing because it's not dissociating. Sugar is built up of covalent bonds. And there's interesting experiments you can do with your roommate, particularly fun to do during pandemic times, is you can take an extension cord and cut off the female end, strip the wires, now plug it into the wall. Okay. Now take a bucket of water, big bucket of water, and it's got to be really, really pure water. But pure water actually doesn't conduct electricity very well. It's actually got a very high level of resistance. And you also want to wash your feet with really clean water as well, no salt. And you step into the bucket and take the wires and stick them in. And you say, hey, we're good. Now, all right, let me just finish the story and I have to pause for a second. Now, you're going to take a handful of sugar and throw it in and swirl it all up, put the electrodes in, you're good. Now get out, have your roommate get in there, he steps in, and you say, look, sugar didn't do anything, hey, let's see what salt does. Throw the salt in, swirl it up, put the electrodes in, it's because the salt has dissociated. It has created an ion current that allows for the passage of electricity like crazy. Don't try that at home.